So we're in this study on vapor cycles to produce power. Think about it as producing a shaft power to turn a electric generator to make electricity and sell electricity. We've talked a lot about reheat and superheat, talked about the effects of the boiler pressure, condenser pressure. Today we're going to talk about regeneration. What's regeneration? Well, the problem currently in our concept of the design is that you have a boiler and the feed water coming into it is cold. It's cold, cold, cold. If you look at the numbers that we were looking at last time, it was like 60 degrees C. I can spell 60. 60 degrees C. And that's not good for performance, especially if the steam coming out is maybe 440 degrees C. There's a lot of heating up of a cold fluid, and that's bad for performance. You would like to get this to be hotter, warmer as you approach or come into that boiler. And we can do a pretty good job of boosting it up to maybe 180 degrees C without burning any additional fuel, without burning, doing anything special, just internal to the cycle. And so that's called regeneration. I'm not certain exactly why. I mean, reheat makes sense. Superheat makes sense. All that. Regeneration, whatever. But basically, you're going to use what they call a feed water heater. Feeding, what's the feed water? It's the water feeding the boiler. And you have something to heat it, to make it go from 60 to 180. And there's two designs. There's going to be the open and the closed feed water heaters. So there'll be an open feed water heater as well as a closed feed water heater that we study. So last time I introduced this, so let's go back and start again. So I'm going to draw this sketch with a open feed water heater. So we have a boiler, and out of the boiler, hot steam, superheated even, and we put it into a turbine. Out of that turbine, you can take it back for reheat and then pass it through another turbine, T2. This would be standard. We then can put it through a condenser, then put it through a pump, and then return it to the boiler. And that would not have any regenerative aspects to that cycle. It would not have an open feed water heater. In this case, I want to contrast it with what we're going to do to improve the system. Think about the pressure and the temperature and that. So at this point right here coming out of the boiler, maybe it's 8 megapascal. That's a number we threw around last time. Maybe it was superheated to 440 degrees C. If we expand it isentropically through that first turbine, but we don't take it down to the condenser pressure, we take it down to 1 megapascal, the numbers will show that it's a very high quality. The quality is maybe 99% isentropic expansion. Can you tell me what the temperature would be if you expanded it to 1 megapascal? It would be the saturation temperature, wouldn't it? And maybe that saturation temperature at 1 megapascal is about 180 degrees C. All right. Now we take it back to reheat. When you come out of reheat, well, you've done exactly that. You put more heat back into it. Maybe you've taken it back up to 440 degrees C. But the pressure remains 1 megapascal. It's superheated, right? Okay. Now if you take it through the second turbine and expand it isotropically to the condenser pressure, and the condenser pressure is 20 kilopascal. Low pressure, that's a number that we've used before. You'll find that the quality is high. I forget the exact number, but the quality may be 98% or something like that. Well, what's the temperature of the steam coming out of that turbine if it's 20% quality at 20 kilopascal, or 98% quality at 20 kilopascal. That's around that 60 degrees C. We then put it through the condenser. What comes out here? Well, it's still 20 kilopascal, but the quality is 0%. What do you mean? It's saturated liquid. That's what we want out of a condenser. What would be the temperature? 60 degrees C. That saturated liquid is fed into a pump. That pump then boosts it up to a very high pressure, 8 megapascal. What would be the temperature of that water coming out of the pump if it boosts it from 20 kilopascal to 8 megapascal? We talked about that last time. It's just a little warmer. It's still around 60 degrees C. There may have been a 0.4, 0.5, 0.6 degrees C temperature increase, maybe 1 degree C temperature increase, but let's say it's 60 degrees C. So that's the problem. This fluid going in is 8 megapascal. That's good, but it's cold. Somebody says, I can change your cycle. I can change your design such that it's going to be close to 180. How are you going to do that? Well, they introduce a feed water heater right here. And the first one we're going to study is an open feed water heater. So let me try and break this line. There'll be the pump coming in, and then it'll be going out like that. All right? So what do is we take a little steam after the first turbine, and we don't send it back for reheat. We just divert it down to feed the open feed water heater. So the open feed water heater has three pipes connected to it, 2 inlet and 1 outlet. All it is a mixing, the simplest heat exchanger. 2 fluid streams mix. All right? So you think about it for a minute. What is this 60 degrees C? That's cold coming in, 180 degrees C there, and you're really going to come out with still 8 megapascal? No, you're not going to anymore. Think about the pressure for a minute. You have 1 megapascal pipe coming down. You have a problem with the 8 megapascal going in right there. Just a simple mixing open feed water heater needs the 2 inlets to have the same pressure. And so you reduce the pressure boost of this pump and you put it down to 1 megapascal. That's a change. That pump doesn't boost it all the way to 8 megapascal. Now it's ready to be mixed with that other 1 megapascal stream. What's going to come out? Well, it's going to come out at 1 megapascal, isn't it? But I need to get it back up to 8 megapascal. How am I going to accomplish that? I'm going to put a pump in there. Here's another pump, and maybe it throws it out that way and goes up. So now we're going to have 2 pumps, pump number 1 and pump number 2. All right. So the second pump will complete the task of getting it up to 8 megapascal. All right. Now, I've used this term happy pump. So if you want a happy pump 1, what do you feed happy to make pump 1 happy? You feed it saturated liquid. If you want the second pump to be happy, what do you feed it? Saturated liquid. And that's the key piece of information that you need to know is, oh, that's what fixes the state going into the pump. That determines how much is diverted after that first turbine to feed this open feed water heater from the top. All right. So if it's saturated liquid at 1 megapascal, what is the temperature of the fluid entering the second pump? Saturated liquid, 1 megapascal. Is it 60 degrees C? No, it's more like 180. It's about 180 degrees C. This makes a little bit of a conundrum because you're thinking, hold it, I've got a fluid stream at 180, that's my hot. I've got a cold at 60. They're going to mix. Why don't they come in at 180 plus 60? What is that? 240 divided by 2. Why don't they come in at 120 as the outlet stream? But it's really coming in out at 180? Can you explain that to me? Do you see my question? If I just said 180 coming in, I'm going to mix it with 60, I'll divide by 2, doesn't that give me about 120 degrees C? Why isn't the outlet 120 degrees C? Can it really be as high as 180? Why is that? How does that work? Because this is almost all vapor. This is liquid, all vapor mixed with liquid, and you're coming out with all liquid, saturated liquid. Oh, there's a lot of energy content of that steam coming down with that high quality. Think about its Hg, its enthalpy of saturated vapor. It's very high compared to the HF. That's how you get it to be so hot. It's coming out at 180. Yep, that's true. All right, now you boost the pressure. Can you tell me what is the temperature of the fluid at the outlet of the pump? About 180. Hey, you picked that up pretty good. It's a modest temperature increase, 0.3, 0.4, 0.5 degrees C, something like that. But it's not a dramatic temperature increase across the pump. All right, so we've done hard work of conceptually thinking through the cycle. Whenever you have a cycle, you need to come in and you need to introduce your particular states. Let's call this one state 1. That's the inlet to the turbine. It's going to be a very important state, and we're going to talk about that mass flow rate that goes into the first turbine again and again and again, and the textbook does too. The mass flow rate going into that first turbine. Okay. Now, what comes out is the same mass flow rate, but then it splits. And you have some coming down here. Well, what do we want to call that? Well, first of all, call this state 2 going out. And then we'll think about the mass flow rate that goes down to feed the open feed water heater. And then the mass flow rate that goes over to the reheat. Right? They're not the same. The sum that goes down to feed the open feed water heater, the mass flow rate feeding the open feed water heater plus the mass flow rate going to the reheat must equal what went into the first turbine, what went through the first turbine. Make sense? Okay. Let's continue with our states, and then we'll come back and talk about mass fractions. This is a unique state right here. This is state 3. That's the temperature at state 3. That's the pressure at state 3. This is a unique state right here. That's state 4. This is state 1 over here. I should circle them. Okay. Here is state 5. Here's a unique state, state 6. Here's a unique state, state 7. And then 8. Now, in my calculations, a lot of time I'll introduce a state 9 and a state 10 for diagnostic purposes, because I want to know still how much energy has to go in this part of the boiler just to bring up the temperature from the 180 up to the boiling point. The boiling point temperature is 295 at 8 megapascal, if you remember that number. So that's a lot of heat still to heat up liquid even before it boils. And then I'll think, what is the amount that takes it from saturated liquid at 295 to saturated vapor at 295? That's a lot of heat too. And then I'll even think about the fraction of heat that's used to superheat it. That's why I introduced these state 9 and state 10 in my calculations. The book doesn't. The other one is, don't forget this heat of reheat. That's the amount of heat to go from state 2 to state 3 in the reheat cycle. So I like to think about the energy coming into the working fluid is in 4 places. 3 associated with getting it into ready for the first turbine, and then the other is the reheat. Okay. So we have all of our states. We have the flow diagrams, and we started talking about this splitting right here. How about, what is the relationship between the mass flow rate that flows through into the second turbine? Is that the same as the mass flow rate that goes through the condenser? Is that the same as the mass flow rate that goes through pump 1? Yeah, all of those are the same. That's the same as the mass flow rate that went through that reheat section. All right. So when they join back together, what goes through the second pump? The mass flow rate in pump 2, is that the same as the mass flow rate that goes into the first turbine stage? When it goes through pump 2, is that the same mass flow rate that goes into the first turbine? Yeah, right. Okay. Now what the textbook does is it introduces a fraction, and they use the symbol y for this fraction. And it's the fraction of the steam that went into the first turbine. It still comes out of the first turbine stage, but then what is diverted down to the open feed water heater. In terms of what we talk about, isn't that fraction, that mass fraction y, equal to m dot, the open feed water heater, divided by m dot T1? Yeah. And isn't this a mass balance for this little control volume where it splits, 1 in, 2 outs? Yeah. And so you can do the simple algebra, and you find that then this is the fraction 1 minus y that continues to the reheat. 1 minus y is the part that goes into the second turbine. 1 minus y is that fraction that goes into the condenser. 1 minus y is the fraction that goes into and through the first pump. But when it joins back up in this open feed water heater, you're back to 100%. It's like y plus 1 minus y is 1. And then 100% is what comes out of that pump, and 100% is what comes into the first turbine stage. So hopefully using this y, 1 minus y, helps you do the mass balance. It's a fast way of analyzing the mass flow rates through the system. We have our schematic. That's hard to do. We have states. We have our components. We know our pressures, temperatures, quality, a lot of that information already, but organize now this information in a property diagram. So in a property diagram, you want to list all of your states. You're going to talk about the pressure, pick one, bar or kilopascal, whatever you like, megapascal. Temperature, Kelvin, degrees C, something. Talk about quality. At some states it's applicable, at some states it's not applicable. Talk about the specific volume, if it's applicable, in meter cubed per kilogram. Talk about the enthalpy, and that's the key property. We work really hard to fill up that whole table on the enthalpies at all the states in units of kilojoules per kilogram. And entropy is needed because we think about the turbine being reversible, pumps being reversible, or if we have to include some isentropic efficiencies for the turbine or pump, you have additional states, a little extra work. But entropy is a key property, kilojoules per kilogram Kelvin. So how many states do we have? We have state 1, state 2, state 3, state 4, 5, 6, 7, 8, 9, and 10. And those are optional. 9 and 10 are optional. So let's do this. I've asked you to take good notes. I want you, I'm going to pause, to fill up the pressure column on your notes. And then put in some of the temperatures that you know from your notes, as well as some of the qualities that I showed. So I'll just start filling out the table here. It was 8,000 kilopascal. Some people are saying, I really prefer to use bar. So, we could put that pressure in bar. How many bar is that? 80, isn't it? Right? It's probably good to do that to make sure that you don't make an error and get confused on your pressures. But okay, so then it was at state 2, it was 1,000 kilopascal. State 3, after the reheat, 1,000. After the second turbine, 20. Hey, what is 20 kilopascal in bar? 0.2 or 0.02? You're good. That's right. It'll save you a lot. Can't make can't make mistakes on pressures during the test. It slows you down, causes a lot of headache. And then state 5, that was after the first pump. It only took it up to 1,000 when you have that regeneration with the open feed water heater. Okay, state 6 is what comes, am I off? No, this is out of the condenser, sorry. Out of the condenser, then out of the pump, and then it comes out of the feed water heater, and then out of that second pump. And again, you don't need to put those other states in if you don't want. 9 and 10 are diagnostic. How about the temperatures? Well, we talked about 440 degrees C. Talk about 180. It's high quality. That quality turns out to be 0.985. What you do is you look up the entropy at state 1, 6.519. You assume it's perfect turbine, frictionless. There's no isentropic efficiency given, so you assume it's 100%. So it's 6.519. Then you use that to get the X, the quality at state 2. You find that it's 0.985. So there's little calculations in there, but that's how you do it. And just like you look up the enthalpy is 3246.1, you can do the same calculation once you have the quality to get this is 2747.6 for the enthalpy. All right. Then we go back to reheat, 440. You look up the enthalpy, 3349.3, and the entropy, 7.5883. It goes through that turbine, second turbine, isentropic, 7.5883, down to that low pressure. You find that it's in the dome. The quality is 0.955, 96%. That gives us a saturation temperature of 60.1. If you really want, this is 179.9 saturation temperature at 1 megapascal. Then you can calculate the enthalpy, 2503.0. Hopefully all those calculations are doable, but let's press forward. You then condense it. So it's saturated, whoops, it's at 60.1. It's at 0 quality, it's saturated liquid. This enthalpy is 25.1.4. You assume that you're going to have this pump is reversible, and so the work of the pump you calculate is VdP. So that allows us to calculate that addition to the enthalpy. So we need the specific volume at state 5. That's saturated liquid, 0.001017. That's our meters cubed per kilogram specific volume of saturated liquid at state 5. Multiply that by the change in pressure in kilopascal, the units work. That'll give you kilojoules per kilogram. Add that to the enthalpy, and you get H at state 6. State 6 is 25.2.4, about 1 kilojoule per kilogram. That's the work of that first pump. All right. Now, this state 6 is compressed liquid, but we have its enthalpy. That's what we really needed. This would be a little over 60.1. You know, it's just a little higher temperature coming out of that pump. The temperature is not that critical to know. The enthalpy is what you do all the work to get. All right, state 7. The big assumption for state 7 is that it's feeding a pump, it's saturated liquid, just like state 5 is saturated liquid because it's feeding a pump. So at 1 megapascal, feeding a pump, that would be 179.9 degrees C for the saturation temperature at 1 megapascal. And that H comes in at 762.8. We need the specific volume because we're going to do the same VdP for the work of the pump. Pump 1 was this one, pump 2 is that one, V delta P, so I need that specific volume right here at state 7. That's 0. I don't want to change color, go back to my same color. 0.001127 meters cubed per kilogram. When you calculate it you find that it increases, so the exit enthalpy is 770.7. What's that? An increase of what? 8 kilojoules per kilogram? Boosting it from 1,000 up to 8,000 kilopascal, or 1 megapascal to 8 megapascal. All right. At this point, you could really stop, but if I wanted to get the saturated liquid and the saturated vapor enthalpies, additional diagnostics would be 1316.6 and then 2758.0. A little bit of work. I think this would be the minimum for a property table that you would want to compute. Now you get another table, which is a table of your energy transfers for each component. Okay, so now we're going to get our table for each component. So what would be a component? How about the first turbine? How about the reheat? How about the second turbine? How about the condenser? How about the pump 1? How about pump 2? And how about the steam generator or boiler? I'm going to call it steam generator. All right. Somebody says, isn't a component the open feed water heater? Why don't you list the open feed water heater? You could, but what we're going to do is we're going to put the heat transfer from the surroundings into it in kilojoules per kilogram, as well as the work out of it to the surroundings. And what we're going to find is it has no heat transfer to the surroundings or with the surroundings, and no work transfer with the surroundings, hence it's a bunch of zeros for the open feed water heater. Now also, these are in units of kilojoule per kilogram. This is in kilojoules per kilogram. So, for the first turbine, just thinking about that first turbine, what is the energy transfer with the surroundings for a well-insulated first turbine? 0. What about the work transfer? We would say you have a high inlet enthalpy, a low exit enthalpy, so the work of the first turbine is a change in enthalpies. That's why we get the table of enthalpy changes, right? And you can compute this, and let me see what it is. It's 498.5 kilojoules per kilogram. Now, I can write them in equations like H1 minus H2, or I can give you the result, which is 498.5 kilojoules per kilogram. But if I give it to you for both, it gets really a messy table, right? So hopefully that makes sense. Now, for the reheat, what happens is you say, well, that reheat, I'm going out at state 3, I'm going in at state 2. You're adding heat to boost its enthalpy. What we find is it's 601.7 kilojoules per kilogram. That's the energy added per kilogram that goes through that reheat section. In a minute, what we're going to want to do is we're going to want to sum to see what Q net is into the cycle. And then we're going to want to sum and see what work net is into the cycle. And then we're going to want to check that these are the same. But what we have to do is we have to talk about the same kilogram that is going to be appropriate for each of these terms. And right away, this kilogram is the kilogram that went through the first turbine. This kilogram is what went through the reheat. We have a disconnect. Let me come back and look at the diagram here. If my mass fraction, if Y was 0.20, 20%, then for every kilogram that goes into the first turbine, how many kilograms go back for reheat? If Y is 0.2 or 20%? 80%. So 0.8 kilograms would go back for reheat. So the first time I'm that you may say, well, how do I do this? Make an additional column and put it, what I would say is Q asterisk. I don't think the book uses this. I think it's helpful if you do it this way. And it's going to be how many kilojoules are transferred in that component. We're analyzing the reheater right now. But it's per kilogram of what went into the first turbine stage. So that when I do a sum here, I'll get the sum of Q asterisks, and it's now all per the same mass flow rate. It's all for the same mass flow rate into the first turbine stage. And I'll have a W asterisk, just like it. It'll be kilojoules per kilogram of what went into the first turbine stage. When I do the sum, I'll get the sum W asterisks. And yes, these will be the same numerically, spot on, the 3 or 4 or how many digits you keep, and there's some rounding errors, etc. But these will be the same, but these will not be the same. Why will the Q and the W net without the asterisk not be the same? Because it's different mass flow rates for each of those components. So you have to put it on the same mass flow rate basis per kilogram going through or into the first turbine. All right. So now I just have to add a piece of information here. Well, guess what? This number doesn't change. It's still 498.5. It's 1 for 1. It's a little trivial on that. But for the reheat, I take this 601.7. There, let me spend a little time on this. So Q asterisk is in units of kilojoules per kilogram that goes through the first turbine. We want to take Q, which is in units of kilojoules per kilogram that goes through the reheat, and we want to multiply it by something so that we get Q asterisk. Well, just looking at units, if I multiplied it by how many kilograms go to reheat compared to how many kilograms go through the first turbine, wouldn't the units cancel and then I get the right units here? So I just have to multiply it by what is that fraction, how many kilograms go to reheat compared to how many kilograms went through the first turbine. In terms of my Y, first clicker question, do I multiply by Y or do I multiply by 1 minus Y? Answer A or answer B. Should I multiply Q by Y or multiply by 1 minus Y to get Q asterisk for the reheat? All right, everybody in? So let's go ahead and stop this. And let's come back to our diagram. Where was it? Here? Okay. If Y is the mass flow rate that goes down to the open feed water heater divided by the mass flow rate that went into the first turbine, right? And I'm interested in the mass flow rate to feed the reheater. I want to divide that by the mass flow rate of the first turbine. That's what I'm really looking for. All right. So I come back to this equation right here and I rearrange it. It's the mass flow rate to go to the reheater is equal to the mass flow rate that went through the first turbine, subtracting how much was diverted down to the open feed water. I put that into this equation right here. So I get the mass flow rate that is through the first turbine minus the mass flow rate that goes down to feed the open feed water heater. I still divide by m dot T1. Isn't that 1 minus m dot naught divided by m dot T1? So, should I multiply by Y or 1 minus Y? Ask the same question. And we'll show the results. And you multiply by 1 minus Y. And the previous one, a lot of you were right the first time, but hopefully we improved it. Now, I need to erase all this. Hopefully you have good notes on this so we can continue on. And so for this one, for this problem, I never did calculate what y was. But y is about 20%, meaning 1 minus y is 0.8 or 80%. And when you make that calculation, here q asterisk drops to 478.6. I can get a more precise value of y in a minute. All right, what about the second turbine? Well, per kilogram that goes through the second turbine, there's 846.3 kilojoules of work produced. But I want everything on what goes into the first turbine. So I multiply that by 1 minus y, about 80%. It knocks it down to 673.2. Let's focus on the condenser. Yes, there's some heat transfer. For every kilogram, there's 2251.6 transferred out of that steam in the condenser. But it's 1 minus y that goes through the condenser as the mass fraction, so it's negative 179.1. I'll try and draw that better. Negative 1, oh boy. Negative 1,000, oh come on. Can't, I'm going to just try it again. Negative 1,791.0. There you go. What about the pump? Well, the first pump really was only about 1 kilojoule per kilogram, but it wasn't out, it was in, so there's a negative in front of it. And when you multiply by 80%, it's negative 0.8. The second pump, though, what goes through the second pump? Isn't it back up to 100%? Yeah. So you had a negative 7.9 kilojoules per kilogram, but I multiplied by 1 because for every kilogram going through the second pump, that's what goes into the first turbine, negative 7.9. Okay, the steam generator, when you make the calculation, is 2,475.4. But that's the first pass through that steam generator. The reheat pass is up here, but we already made that correction there. So this is just 2,475.4. So 1-to-1 for that pass from, this is steam generator first pass. It goes from what, state 8 to state 1. Now if we do the sum of the Q asterisks, you pick up 1163.0, and the sum of the work asterisks 1163.0, meaning for every kilogram that goes into the first turbine stage, there's 1,163 kilojoules of work produced out of the power plant. And there's a net Q of 1163. Now, that's not all that important. What's most important is I had to purchase this. And this is what we call thermal pollution. Isn't it? Thermal pollution? So that's not neat. It's just heating up lake water or heating up river water or heating up ocean water. We don't want that, so get rid of that. So now, if all of these are true, what are the metrics of interest? What is the back work ratio for this plant? The back work ratio would be, well, I have to go back and feed my pumps. So it's going to be a negative of negative 0.8 plus a negative 7.9. And I shouldn't have scooted down that much, but right here, it's the work out of the turbines, isn't it? The sum of those two, which is, I'll try and write it, 498.5 plus 673.2. That comes in at point something percent. 0.74%. That's less than 1%. Then the next one, what is the thermal efficiency of the plant? Well, you don't divide, you get W net, which is 1163.0, but you don't divide by Q net. That would give you 1. No, you divide by what you had to purchase. You had to purchase 2475.4, and you had to purchase 478.6 in the reheat and the first pass. And that thermal efficiency of the plant comes in at about 39%. This comes in at about, this is a 2 right there, about 39.4%. All right, sorry about the sloppiness, but I know that if I start switching too many screens, students, it's hard to see everything, okay? Hopefully that helps. One thing we didn't do, did we? We didn't say, how do I calculate that fraction? So let's do that right now. This is my open feed water heater. We're bringing down the mass flow rate to feed the open feed water heater. And it's coming from what state? Wasn't that state 2? Okay. We're coming in state 6. Is it state 6? Yeah. State 6. And that's the mass flow rate that basically goes through the reheater, which is the same as the mass flow rate through the second turbine, same as the mass flow rate through the condenser, same as the mass flow rate through the first pump. You know, there's ways you can describe that. But then it goes out at state 7, and we have this as the mass flow rate that goes through the first pass of the steam generator, or just put M dot T1. That's what goes into the first turbine stage. All right. Hopefully all that makes sense. You're able to say that we want H7 to be saturated liquid at that pressure. That's assumption. We want a happy pump, H7 saturated liquid. So H of F at that pressure. Okay. And we are able to get H of 6 and H of 2. So we know our enthalpies. So let's do this. Let's write out our mass balance equation. It's pretty simple. It just says that the mass flow rate O coming in from the top to that open feed water heater plus the mass flow rate, I don't know, how do you want to draw this? Just call it the reheat. You know, reheat, second turbine, condenser, first pump is equal to the mass flow rate that goes into the first turbine stage. Does that make sense? All right. Let's do our energy balance. All right. What's our energy balance look like? Well, I'll take the enthalpy at state 2 times that same mass flow rate, feeding it. I'll take the enthalpy at state 6 times the same mass flow rate through the reheater, and those two sums must equal the out. Those are the two ends. The out is the H7 times the mass flow rate first turbine. Did I make a mistake yet? Everybody okay? So what you want to do is maybe just do some algebra. Maybe I rearrange this to say that the mass flow rate through the reheat is the mass flow rate first turbine minus mass flow rate down the open feed water heater. Substitute that right in here. So I'll have H2 M dot naught plus H6 times M dot T1 minus M dot naught equal to H7 times M dot T1. Maybe at this point you multiply everything or divide everything by M dot T1. M dot T1, M dot T1, M dot T1, right? You just multiply the whole equation, divide it by mass flow rate through the first turbine. And now what does that look like? That looks like H2 times, what is this fraction right here? What's that fraction? It's Y, isn't it? Okay, how about this one? You have H6 times 1 minus Y, right? And then you have H7 times 1. Actually, when you get good at it, you almost just say, hey, my combined mass and energy balance, I can write it like that because this is my mass fraction Y coming, this is my 1 minus Y mass fraction, and this is my 100% going out. Okay, but we did it in a few steps of algebra. Now you could solve for what Y needs to be. y needs to be H7 minus H6 divided by H2 minus H6. Is that what y needs to be? Algebra. Based on mass and energy balance. Did I lose anybody? You okay? All right. Ready to press on? All right. Might as well just throw you into a big problem, right? That's how you learn. You just have to solve problems. So this is a problem. Water is a working fluid. Good. Regenerative vapor power. When you see that, you know you have at least one feed water heater. It's coming out and enters that first turbine at this pressure temperature. It exits the first turbine at a lower pressure, 2 megapascal. Some steam is extracted to feed a closed feed water heater. So right there you have a closed feed water heater. While the rest is reheated. Good. Then it hits a second turbine. But it exits the second turbine at 300 kilopascal. That's not our condenser pressure. Some of the steam is extracted to an open feed water heater. So I have two feed water heaters, a closed and an open. It's getting more complicated. The rest is reheated. I have two reheats. And then it expands to a third turbine. Oh, this is too complicated. And then finally it hits its one and only one condenser. But it's at this nice low pressure of 20 kilopascal. That's good. And then they give you some information about the closed feed water heater. After the closed feed water heater, the condensate is put through a steam trap. And after the steam trap, it goes to the open feed water heater. This gets really complicated. Let me start drawing it out, okay? So you have some big steam generator. You're going to take a pass through it and come out ready to go into the first turbine. After the first turbine, you're going to split some and go down to a closed feed water heater. So down here will be a closed feed water heater that you're going to feed. Okay. This will go out and go back to reheat. We're going to call that reheat 1. Then it goes into the second turbine. After the second turbine, it splits. Some goes down to feed an open feed water heater, while the rest goes back. You got to be joking me. There's a lot of plumbing in this here plant, isn't there? For reheat number 2. A lot of pipes. You can get really confused in an actual power plant. A lot of pipes. And then you go to this third turbine stage. After the third turbine, you go into a condenser, finally. Saturated liquid coming out, like to put it into a pump. And in the pump, we'll feed that open feed water heater. All right, so let me kind of connect this one up right here. That'll go like that. After this open feed water heater, we're probably going to put a pump, then shove it like that into the closed feed water heater. What's the difference between an open and a closed feed water heater? They don't mix exactly right. They don't mix. And so what happens is the fluid, think about this one staying in the pipes of that closed feed water heater. Maybe I'll clean that up a little bit. It stays in the pipes. Maybe it splits and it has a manifold to distribute it, a manifold to collect it, and there is a bunch of pipes that it runs through, or tubes that it runs through. But it doesn't mix with the stuff that's on the outside of the tubes. So you have a shell side and a tube side to this heat exchanger, this feed water heater. Then it's collected up and then it goes back out. Okay, so this stays on the shell side. And then this stays in the tubes. All right. Now, because it stays in the... let me do this one. Let me introduce some states so I can start talking about the states. What do you think we should call that? State 1. How about this one? State 2. How about after the reheat, state 3? After the second turbine, state 4. After the second reheat, state 5. After the turbine, state 6. Then we have state 7, state 8. And I know I'm making this look too easy, but there's a lot of decision points in this. Okay? Then state 9 right here. Now, quick question. Can you tell me a little bit about the pressure at 4 and the pressure at 8? Are they equal? They need to be. How about the pressure at 9? That's your understanding of an open feed water heater. The two inlets have the same pressure as the outlet. Right, very good. So this is P9. All right, now we go to state 10. All right, can you tell me a little bit about the relationship between the pressure at 10 and the pressure at 2? They do not have to be the same. They're typically different. That's why they have a closed feed water heater. The fluid inside the pipes can be higher pressure than the fluid outside in the shell. That'll be the case for this heat exchanger, but it could be opposite too. All right. So now that you come out, this is state 11 right here. Now, you'd really, if you're an engineer, do you want a lot of pumps? You already have pump 1. You have pump 2. You really don't even need another pump because this is ready to go that way. You could put the pressure at 10 could be the same as the pressure at 11, could be the pressure at 1. That's a very common assumption. All right. So this is a good way of doing it. Now, what do you do with this fluid? Remember, this is like a high quality, maybe 100% quality or slightly superheated steam. It's a lot of energy content. When you put it in the shell side, what you're going to do is you're going to collect the condensate. And so you're going to want to take, this is state 12 coming out, and it's going to be saturated liquid at the pressure of the shell side, or pressure 2. That's a high pressure typically. What are you going to do with it? Well, you put it through a device that's sketched like this, and that's called a steam trap. First time you hear that term, you'd say, well, I don't understand what that is. Think of a policeman who directs traffic and will only let through the intersection condensate and no vapor. So basically, it's you can easily see these demonstrations of the steam traps on YouTube or other places. And I don't have enough time maybe to go show you right now, but basically you'll have a float determines the level of condensate. And so when the level gets too high, it opens the valve and there's a pressure drop and it goes through. But when the condensate level is low, the float level falls and then it shuts it off. It's a pretty easy steam trap. All right. Even though the steam traps may be simple in concept, believe me, a lot of engineers don't really know what they do. And a lot of plants have failed steam traps. If you ever are around power plants and you are asked to diagnose or go find problems, if the operators know what they're doing, they'll have already fixed all their problems with steam traps. But go and look there first, because these will fail in the open, and what will happen is you'll have a vapor going through. They'll get stuck and they'll just let vapor through, and it'll mess up the operation of the plant. How do you tell? Actually, you just listen to it. And if there's a lot of machinery around, they have machines that allow you to put something on it and then listen. What do they call those? Ultrasonic type of amplifier. So you just listen because condensate going through will be on, off, and then it sounds different than stuck open with steam rushing. Okay. That's how you figure it out. All right. So now that you've dropped the pressure, this is an additional state, 13. Maybe you drop it to a low pressure. What are you going to do with it? You got to do something with it. Why not drop it to the low pressure of the open feed water heater and dump it in there? Yeah, there you go. So this is a complicated plant. You got your states down, you kind of got your plumbing down, you got your components down. Let's do our mass fractions. So we're going to walk through and say 100% goes into the first turbine. And then we're going to divert some. Maybe call this Y coming down. So what continues to the first reheat? 1 minus Y. What goes into the second turbine? 1 minus Y. But you now have additional diversion. Well, maybe that's the same fraction that gets diverted. Maybe it's 20% here. Not likely. Those Y's are different. So you could call this Y1 and Y2. The book may do that. I think the book does this one. What do they do? Don't they put Y prime and Y double prime? Who has a copy of the book open? Looking at following. What do they have? Y prime and double prime? Does that mean a differentiation and a second derivative of Y? Hey, that's another math class or a different engineering class. No, that just is, I would have maybe put Y1 and Y2. But then they would have said, well, is that Y for state 1 and Y for state 2? Okay, fine. Let's go with prime and double prime. You know, there's just like, what syntax and notation are you going to pick? Now, so if this, here's a good question. What again was Y prime? Was it the mass flow rate that goes and feeds this closed feed water heater divided by the mass flow rate that goes through the first turbine? Yeah. Okay, Y double prime. Would it be the mass flow rate to go to feed the open feed water heater divided by the mass flow rate that went into the second turbine? It's okay if you would say that, but that's not what the book uses. And if you use this, it's a little more complicated. If you use what went into the first turbine, put a 1 there, it'll make life a lot easier. So if you use this for the definition of Y double prime, then guess what continues back to the second reheater? 1 minus Y prime minus Y double prime. It does. Makes the math a lot easier on what continues in the loop. Likewise, what goes through the condenser? 1 minus Y prime Y double prime. What goes through the pump? Number 1, 1 minus Y prime minus Y double prime, right? So we got Y double prime feeding this open feed water heater from the top. What do we have going through the steam trap? Y prime. What feeds the open feed water heater from the bottom? Y prime. I have 3 inlets to that open feed water heater. 1 outlet. What is the mass flow at not going into the second pump at 9, you know? It's back to 1. Yeah. And then it's 1 going out of the pump, and then 1 going into the steam generator for that first pass, and then 1 going into the first turbine. That is a big step. I don't know how to say it. I tried to explain it the best I can. You have to grapple with it. Please understand it. One of the things that you might be tempted to say is, hey, we should have Y double prime is the mass flow rate that goes into that second turbine. Don't do it. Keep everything as to what goes into the first turbine. And your life will be a lot easier. Okay? Yeah, that's right. 1 minus Y prime on that first reheat. That's right.
I have a question.
Yes.
So after the open feed water oh, that's Y prime.
Yeah, it's Y prime from the bottom, Y double prime from the top, and 1 minus Y prime minus Y double prime.
What goes into the steam trap? How is that the same mass flow rate of what comes into the closed?
This is what is feeding the closed feed water heater. This is what feeds the open feed water heater.
Leaving the steam trap.
Yeah, so this is M.C. This is M.C. It stays in the shell side of that heat exchanger. There's no mixing. It's a closed, that's right, closed feed water heater. Yeah. All right. When you analyze this problem, what do you think you should do? Make a table of states and your properties, and the key table is the column of enthalpies. You have to get the enthalpies, you have to get them correct. All right. After the enthalpies, you can actually then get your y and y double primes calculated. You'll need that when you get your energy transfers. At this point, we can calculate our y prime and y double prime equations. How am I going to get my y prime and y double prime equations? I have to scoot down here to make more room. There's the definition of them. What do you think I'm going to do to calculate, to find out, oh, y prime needs to be 13% and y double prime needs to be 15% or whatever it is numerically? How am I going to do that? I'm going to do an EB balance. So a mass balance as well as an energy balance. So if you do it for the closed feed water heater, let me kind of draw it like this. There's my closed feed water heater. And I'm going to do it a little simpler or faster. Maybe I should go really slow. Okay, let's vote. Really slow, show your hand. Really fast, show your hand. All right, a lot of people are sitting on their hands. We'll go slow. We'll go slow. All right. So let's do the mass balance. We have the mass flow rate feeding it from the top. But you know what goes out the bottom? To the steam trap? The same amount. And then what do we have over here? We have the mass flow rate coming out of the pump 2. That's coming in on the tube side. Guess what? That's the mass flow rate that went through the second pump going out the tube side over there. All right, not too exciting, is it? But I could substitute this by saying that's T1 and T1, couldn't I? Okay, I'm going to have a hard time, harder than I think on this. Let me do the energy balance. Okay, for the energy balance, we have the H2 times the mass flow rate feeding it on the shell side plus the H10 times the m dot T1 equal to the H12 times m dot C plus the H, is that 11? M dot T1. Does that make sense? All right. Really, the mass balance is so trivial, I hardly need it. All I do is take this equation and divide each term by m dot T1. M dot T1, m dot T1, m dot T1. I need to scoot down a little bit, sorry. So as I scoot down, this equation, energy balance equation, becomes H2 times y prime. Isn't that our definition of y prime? Plus H10 times 1 equal to H12 times y prime plus H11. At this point, I can get y prime is equal to H11 minus H10 divided by H2 minus H12. Did I do the algebra correctly? Okay. Maybe the mass balance will be a little trickier for the open feed water heater. Let me do this. Let me see if I can do this. I'm going to grab this. I'm going to do it like this. Grab that. And then do a edit, copy, 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 copy. Come over here to a new page, edit, paste. Control V. All right. What I want to do now is I want to do a mass balance and an energy balance for that open feed water heater. And I wanted to get it to another page, okay? So I just copied it over. All right. Now, let's talk about our mass balance. So we have the mass balance, the mass flow rate feeding the open feed water heater from the top. We have the mass flow rate after the pump 1. That would be at state 8. Plus the mass flow rate at state 13 feeding it. Maybe I'd put these all as the states. The mass flow rate coming from state 8 the mass flow rate coming from state 4, the mass flow rate coming from state 13, and they all join up and make the mass flow rate going out at state 9. Does that equation look okay? Reasonable? Good, thank you. Now, what about our energy balance? H4 m dot 4 plus H8 m dot H plus H13 m dot 13 equal to H9 m dot 9. Right? Okay. Whew. All right. Do this. If I divide the whole equation here by the mass flow rate of the first turbine, what is this ratio right there? The mass flow rate coming from 4 divided by the first turbine, isn't that H4 times Y double prime? Then you have H8. What is this? It's what? It's going to be 1 minus Y prime minus Y double prime. And then you have the H13 times the M dot 13 divided by, isn't that Y prime? And that's equal to H9 times 1. All right, maybe I shouldn't have changed colors so much. This is H13. Okay, so now what I can do is I can solve for Y double prime, knowing all the enthalpies, plus I have to have already solved for Y prime. So Y double prime is going to be H9 minus H13 times Y prime minus H8 times 1 minus Y prime divided by H4 minus H8. Did I do that okay? One yes. Any other yeses? Little tedious, but you got to get this right, okay? You have to, double check it, but it's just energy and mass balance. Did I do it okay? Looks like I'm done for my time. Thank you very much for your attention.